Okay, welcome back. This is going to be a math interlude. So this is kind of a pause from content, but making sure that we have some of the fundamental math skills and understanding to be able to work through things this semester, and even into next semester. Okay, so we're going to start with really making sure that we understand integrals. Now, I'm not going to go over all the rules of how to take complicated integrals by hand. Instead, we're really going to focus on making sure that we know how, when we use an integral, what that means. So, there are really two types of integrals. There's a definite integral, and this is an integral evaluated between two limits. And so this is whenever we say a to b. And then there's the indefinite integral, and that's just saying I generically want to find the expression of the integral of this function. We will not really be using indefinite integrals much this semester. But if you remember from calculus that when we take the integral of indefinitely, we get out an answer that is a function, let's call it g of x, and we have to add this constant because we don't know anything about this. But whenever we do between limits, that this constant becomes much less of a problem. Because in this one, our answer is still going to be g of x, but we are going to go from a to b. And so that gives us g of b minus g of a. Remember this? Vaguely? To evaluate the integral, you're going to use the rules that you learned in calculus. Now, many times, especially during the semester, we're going to run into functions that are really tough to integrate. We need u sub, we need trig rules, we need all sorts of stuff that you probably learned in Calc 2, but I definitely don't remember it, and you probably don't either. And so really, before you try doing any fancy integration by hand, you should really start working on pulling up some tools. So there's an integral table that is found on World Class. There's Wolfram Alpha. And if it's something that I'm assigning you, there's Google Colaboratory, which is a coding platform, and a lot of complicated things I'm going to code for you on this. But if you happen to know some Python, this is a tool that can work for you. I do not expect you to know any Python. Okay, so what does an integral mean? Integrals determine the area under a function. So if we wanted to, we have a Maxwell-Boltzmann distribution of helium at 100 Kelvin, and say that we wanted to know the number of molecules that have velocities between 0 and 3,000 meters per second. The way that we could find this is that we could ultimately be working to find the area that fills in under the curve between 0 and 3,000. Because remember that this is a probability distribution, and so that means that these are bins or counts of molecules along the way. And so if we knew the number of molecules in each of these bins, we could really just add them up and get our final answer. And it turns out that this integral is this adding up of these numbers. So what is actually happening? Well, the function graph that we were making using the equation, for example, this probability distribution or the Maxwell-Boltzmann distribution, that is the graph. That is our f of x. Okay, so this is our distribution or our function that we are interested in. The limits on the integral, these are on the x-axis. So this is really our 0 to 3,000 meters per second. So it's our x-axis limits. The d of whatever variable, in our case was d nu, was what we are integrating over. This is going to correspond to the x-axis, and it really is describing the step size that we are taking in the calculation. So if you remember the trapezoid rule, it's saying that we are creating these tiny little bends. We're finding the height of those bends and we're adding them up. And that there's this piece where we leave some out on this side, but we have some extra on this side, and so they start canceling each other out, and we can get the area under this curve. And this is what the integral is really doing. Why is this helpful? Well, it really relates to physical properties or measurements. The area under a Maxwell-Boltzmann distribution corresponds to the number of molecules in a sample that are moving with the velocities between the limits of the integral. So whenever you see this y-axis is going to be helpful. So when we see probability is really a count. Now, it's sort of a fractional count, like part per whole, how many molecules are, what percentage of the molecules are moving with this speed. But it is a count. And so if we can integrate over a probability distribution, we can get a number of molecules. But that resultant is going to be related to your y-axis, and so keeping an eye on that is going to be important. Okay, so your now try this problem is to write the complete integral expression that should be solved to find the number of molecules in a sample of oxygen gas traveling at speeds between 200 and 800 meters per second. Your final expression should include all necessary numerical values, but does not need to be simplified or solved. And you can find this equation on page 53. And I just realized that we forgot a temperature. Let's say temperature equals 300 Kelvin. Okay, now remember that I post the keys to these Now Try This problems on World Class. And stay tuned. In our next video, we are going to be talking about figuring out the average of a distribution.